Hi everyone, my name is Hamid Gorgiara from UC Irvine, and today I'll be presenting Jaaru, an efficient model checker for persistent memory programs. This is the joint work with Harry Zhu from UCLA and Brian Dembski from UC Irvine. Recent persistent memory technologies such as Intel Optane memory attempt to provide the performance of DRAM with the persistency of flash storage. Persistent memory can interface with the processor via the memory bus, which provides byte addressable access for a program with regular load and store instructions. With persistent memory, the program can use a single copy of data structure, both as an in-memory working data and as a persistent store of data. This new way of data manipulation is very efficient due to eliminating the overhead of serialization and deserialization process. However, this efficiency comes with the main challenge of system crash happening when the program is running. This is challenging because stores are not immediately written to persistent memory. They are initially written to the volatile processor cache, and the persistent memory is eventually updated when the cache line is written back due to space constraints. So the order a write becomes persistent can be different from the intended program order. Modern processors provide special cache instructions such as CL-flush to force the ordering by flushing cache lines to persistent memory. However, using these instructions correctly is challenging and error-prone by itself. It requires both subtle reasoning about the ordering of memory operations and attention to not miss persisting of any stores in the program. So testing the correctness of persistent memory programs with respect to failures is very difficult and very important. As evaluation on previous work suggests, naive model checkers face scalability issues in testing persistent memory programs. We investigated such programs and we made an observation that makes model checking practically feasible for them. In fact, we observed that these programs need a way to determine which data has been written out to persistent memory. The common technique is to use commit stores. These commit stores indicate that prior stores have been successfully flushed to persistent memory, and in post-crash, the program just reads from these stores to determine the data is consistent. For example, in adding a new node to the root of a tree, the program first creates a new node and updates its value and references. Then the node is flushed to persistent memory. Finally, the program updates the pointer from the root of a tree to the node. This pointer is a commit store. In post-crash execution, if this pointer isn't null, it shows the insertion operation was successful. But if the pointer is null, there is a lot of possible memory states in post-crash, but all these memory states correspond to one unique post-crash execution, and that is the insertion operation fail. Our insight is to leverage commit store pattern and enumerate executions instead of memory states. Based on this insight, we implemented Jaaru, a fully automated efficient model checker for persistent memory programs. Jaaru exhaustively explores all possible executions. It doesn't require any annotations on the program, and moreover, it doesn't generate any false positives or false negatives. Any bug that it reports is a real bug with the corresponding execution trace. Jaaru is capable of simulating complicated crash scenarios with more than one crash for testing the recovery code. It uses a constraint-based refinement technique to reduce the search space. The idea is to reason about the last time each cache line was written back to persistent memory. To be more specific, Jaaru uses sealed flush instructions to infer constraints on the last time each cache line became persistent in pre-crash executions and refine these constraints in a post-crash execution. This technique works well for persistent memory programs because it effectively leverages commit stores. In fact, Jaaru does not eagerly enumerate all pre-crash stores. Instead, it lazily enumerates a small subset of them that are actually read by a post-crash execution, which is the key idea to drastically prune the search space in Jaaru. To use Jaaru, the persistent memory program has to be compiled with Jaaru's LLVM frontend, which instruments memory and cache instructions. Then, after running the program, the scheduler identifies potential crash points, and the runtime system runs the program and simulates crashes. Jaaru analyzes the execution and refines the corresponding constraint for each cache line. If it finds bugs in the program, it reports them to the user. Otherwise, it repeats the process until there are no more executions. Jaaru can identify different types of bugs, including missing fences, misordered flushes, and misordered stores that cause atomicity violations. We've evaluated Jaaru with popular recipe and PMDK benchmarks, and we found 12 and 6 new bugs in these benchmarks. Jaaru is now available on our website for the public usage. Thank you.